Hanneke Gelderbloem.
So good evening everyone. So my name is Hanneke and in my daily life I'm a scientist at the University of Twente and my research field is the physics of fluids, and today I would like to talk to you about a fluid which I think everybody knows very well and uses a lot, which is coffee. And now you might wonder what is so special about coffee. Well, I think actually everybody is kind of familiar with the effect if you spill coffee on your table and you look at the droplets, then initially they're uniformly dark in color. But if you wait a bit and you come back later, your droplet has dried, and what you will see is that a dark ring has formed, and in the inside it's very light. Now this effect is not really specific for coffee, but it can happen with all different kinds of fluids. So here you see some examples. And what these fluids have in common is that they consist of liquid with small, tiny particles suspended in it. And somehow due to the evaporation of the drop, all those particles move to the outside, and they form these ring-type patterns. Okay, so the next slide will show you an example where people in industry actually suffer from this effect. So this is an example from inkjet printing. People would like, of course, to print uniform patterns, but what they see in their droplets is that all the color accumulates at the edge of the drop. So here they really don't want this effect. So it's a very generic effect. It can occur with many, many liquids, but the official scientific name for it is the coffee stain effect. And, yeah, seriously. The two things I would like to explain to you in this talk are, first of all, how come? So why do we see these kind of patterns? Second, can we understand the type of pattern that forms, and can we also control it for applications in, for example, nanotechnology? So the key in understanding why these patterns form is in understanding how droplets dry. And this is in a very non-trivial way. So if you calculate how fast the droplets rise, what you will see is that it dries a lot faster at the sharp edge of the drop, where I drew the circle over there, and a lot faster there than in the center. And this rapid dehydration from sharp edges is something that you all know, in fact. If you roast potatoes in your oven, I think everybody knows that it burns first at the edges, and this is also because there the dehydration is a lot more fast. So something similar happens in our coffee drops. They dry a lot faster at the edge, but at the same time they want to keep a spherical shape. So this means that somehow you have to refill the fluid that evaporates from the edge. And this causes a flow inside these droplets, from inside to outside. And this flow drags along the particles, then they arrive at the edge of the drop. There the liquid evaporates and the particles remain, and they form these very nice coffee rings that you all see on your tables. So we wondered if we can also see this in an experiment. So we did an experiment with fake coffee, so it's just water with small 1 micron sized particles in it. And we observed it from the side with a camera, so here you see some stills. And you see the droplet rise, it becomes flatter. And at the same time, we looked from below through a microscope if we could see the motion of those particles. So here you see examples of all these particles that are the white dots. And you see some arrows which indicate the direction of motion from inside to outside. And what you also see is that they go faster, because the arrows become bigger, as the droplet gets smaller. So the more the droplet dries, the faster these particles start to move towards the outside. So we can also measure this exactly. Oh, this doesn't show very nice. Okay, so there's supposed to be a velocity on one axis, and then there's time. So what you see is that the speed of the particles increases over time, and we can also calculate that exactly. That's the green curve that you see. So we can really model what goes on in these coffee drops. So to understand why everything goes faster at the end, there's a simple analogy. I think everybody knows if you water plants in your garden and you squeeze the hose, is that the liquid speeds up because you squeeze the same volume through a smaller gap, basically. Now a similar thing happens in our coffee drops. They evaporate, so you have a constant flow, a volume of liquid that comes to the edge, but it has to be squeezed through a smaller and smaller gap because the droplet becomes flatter over time. So the same thing here. The droplet becomes flatter and the speed of the particles increases. And this will be of influence for the type of pattern that you can form eventually. So if we look at the stain that remains, okay, there should be a very nice picture of a stain here, which doesn't work. Okay, so there should be a ring stain. I think you believe me that the particles have moved there. And I hope my next slide, I think it will be okay. There you can see that the particles have erased in a very peculiar way. Yeah, so here it is. So what you see is that inside the stain, so this is now a zoom of the ring, the particles have a very disordered arrangement, whereas outside, so the outermost layers, the particles have a very beautiful crystalline way of organization. You really see it here. So the particles have by themselves arranged into this packing structure. And so this also doesn't show well. Okay. So, okay, what I wanted to explain here is that the way these particles are packed reminds one of the way oranges are stacked at the market. And this is the most dense packing that you can achieve with hard spheres. And our coffee particles have by themselves arranged into this configuration. Okay, this is also not correct. Okay, in any case, what I wanted to explain here is how come that these particles can order. So if they arrive very early in the life of the drop, they have a lot of time to arrange. So when they arrive at the drop edge, they have time to explore space and to find the most efficient spot. So you get ordered packings. Whereas so here you're supposed to see that when particles arrive very fast, then they don't have time for arrangement. So it's like in the computer game of Tetris. If you have a lot of time, you can arrange your particles, you get a nice pattern, whereas if you have very little time, you get disordered packings. So what we can do is we can calculate when this transition happens, because it depends on how much time your particles have to arrange. And by this we can also control the size of the ordered domains that you form. And this is very important for nanotechnology applications where people want to make very tiny structures of nanoparticles by self-organization. So with this I would like to conclude this talk, and I hope to have shown you that there's actually a lot of nice physics in your life.